Hi guys. Hope everybody survived the test. Isn't too traumatized. This class doesn't get a whole lot harder than that. At least not this semester. Second semester there are some slightly more difficult things, but like I said before, do your homework, pay attention to the lectures, and you're going to be fine. So chapter 2 is kind of the chemistry you need to know to understand biology. So the first section, the nature of matter. What are we made of? Obviously, everything around us is made of some sort of chemical compounds, and we are too. So starting off with atoms, my first grader learned about these this week, so hopefully you guys are all very familiar with atoms. The particles that make up atoms, protons, neutrons, and electrons. The atom is the basic unit of matter. This guy named Democritus came up with this idea. He basically said, at what point can you keep cutting things down before it stops being matter? And so he decided that very smallest thing that can still be considered matter is an atom. I had to find a picture of Democritus because the notes I used to use had one, and he is just a really creepy looking dude. So there's Democritus. Atoms are really small. I hope we already know that. Clearly, the subatomic particles that make up atoms are smaller than the atoms. There's a nice little picture that shows you the three subatomic particles. Protons and neutrons have about the same mass. Protons are positive, neutrons are neutral. Together, they make up the nucleus. The electron is negatively charged, and the electrons float around the outside of the nucleus. Atoms are normally going to have equal numbers of electrons and protons, so that the positive and the negative will balance out. And then the atom will be neutral overall. Isotopes. Isotopes, hopefully you talked about in physical science last year. They all have the same number of electrons, so they should have the same chemical properties. Element is a pure substance made of just one type of atom. So carbon is made of only carbon atoms. There's over 100 elements. I hope you've all seen a periodic table. There's only about 24 that really apply to living things. I'm sure you guys have all seen chemical symbols before. C is for carbon, H is for hydrogen. If not, go look at a periodic table. They're all there. The number of protons in the nucleus is the atomic number. So for carbon, that number would be 6. And since there's 6 protons, there's got to be 6 electrons to balance that out. So isotopes, they're going to have the same numbers of protons and electrons, but a different number of neutrons. So this chart is showing carbon-12, carbon-13, carbon-14. They each have 6 protons and 6 electrons, but the number of neutrons goes up. So if you look here, carbon-12 and 13 are not radioactive, carbon-14 is. So that's important because they use it for radioactive dating. The mass number is the total number of protons and neutrons. So that's where this number comes from in the isotope. So carbon-12 is called carbon-12 because it has 6 protons, 6 neutrons. Carbon-14 is called carbon-14 because it has 6 protons and 8 neutrons. So those are their mass numbers. The atomic mass. If an element has a bunch of different isotopes, the atomic mass for that element will be the average of the isotopes. And when they do that, they consider how much of that isotope actually exists in nature. Like I said before, some isotopes are radioactive. Their nucleus isn't stable. It's going to break down over time. And that's why they can use it for dating fossils and basically anything they find that's really old. And this is probably a little more applicable to the average person. They can use radiation from different isotopes to treat cancer. So, my mother had a lot of radiation treatments like 7 years ago. She had cancer. I'm sure you all know someone who's gone through radiation. They can also use it to kill bacteria in food. So that's kind of convenient. Okay, chemical compounds. I can't emphasize this enough. The properties of a compound are usually going to be really different than the elements that form that compound. They give the example of sodium. It's a metal. It's really soft. Chlorine, poisonous gas. You've probably talked about that in history. And then you put the two together, you get table salt. Totally different than either one. Not dangerous at all. So a lot of compounds are like that. The compound is totally different than either one of the elements that form it. Chemical bonds. Hopefully you've heard of ionic and covalent bonds before. Valence electrons. Those are the electrons that are able to form bonds. So an ionic bond, electrons are transferred from one atom to another. So in a salt molecule, the electrons are going to go from the sodium to the chloride ion. And that happening causes the sodium to be positively charged and the chlorine to become negatively charged. When that happens, those are each called ions and not just atoms anymore. So transferring that electron from one to the other is going to bond them together. We're going to scroll through that real fast because this should be stuff you covered in physical science last year. Covalent bonds. So this is where atoms are going to be sharing electrons. If they're just sharing 2 electrons, it's called a single bond. If it's sharing 4, it's a double bond. If it's sharing 6, it's a triple bond. So covalent bonds form what we call molecules. It's the smallest unit of a compound. So the water molecule is used a lot of times as an example of covalent bonds because these electrons don't really belong to the oxygen or the hydrogen. They're floating around amongst all those atoms. Sometimes covalent bonds form between 2 atoms of the same element. Oxygen is a compound formed with covalent bonds. The oxygen in the air is usually diatomic oxygen, so 2 oxygen atoms with a covalent bond keeping them together. Van der Waals forces. The water molecule is a good example of unequal sharing of electrons. Let me go back to that a second. Because of the way these atoms are designed, the electrons are shared, but they're not shared evenly. We'll talk about that more in a later lecture, but when that happens, sometimes it causes parts of the molecule to be charged. So when these charged molecules are close to each other, they might be attracted to each other. This is called Van der Waals forces because some guy named Van der Waal discovered them. They're not real strong, but they can hold things together. And this applies to biology because, like a gecko's feet, they can climb up the side of a window because of Van der Waals forces. So that's the start of this chapter. Hopefully 98% of that was a review from physical science. But if not, there it is.